Hello and welcome to another wonderful adventure of the New York City Category Theory Seminar. Today we have the honor of having Michael Shulman, and he will talk about the derivator of setoids. Anyways, Michael, take it away. The four things, please, go.
Yeah, right. Thank you. So I was born in Los Angeles in the San Fernando Valley, and I did my bachelor's degree at Caltech in Pasadena, a little ways away, and then I went off to Chicago to do my PhD under Peter May. So that's my background in homotopy theory and algebraic topology. And then I became a category theorist. And well, I was always a category theorist, but sort of secretly. But then I became more of a category theorist and a type theorist. And now I'm here at the University of San Diego back in Southern California.
Would you say that Peter May is also a category theorist?
Well, he probably wouldn't. But if you understand category theory broadly as including higher category theory and homotopy theory as a part of higher category theory, then I would argue that probably he is. I mean, he's certainly done plenty of ordinary category theory too. But I mean, he would probably describe himself as an algebraic topologist.
Right. Emily was there at the same time you were, or she's
That's
younger?
right. Yeah, she was. She's a little bit younger, but we overlapped a lot.
Yeah. She's also his student.
Mm-hmm. Yeah.
Okay, thank you. Take it away. Perfect.
Okay, thank you. So thanks very much for the invitation. I'm happy to be here, in whatever sense I am. I must apologize also if I'm a little bit discombobulated. I drove up to LA and back the past couple of days, and then I'm just coming off of 5 straight hours of teaching and meetings, and so I'm here I am, but I don't know how well we'll do. But I'm happy to talk to you about this stuff. And so if I'm going slowly, that's great, because maybe people will understand me better than when I go faster. So I don't have prepared slides, so I'll just be writing, and you can stop me if whatever I say is confusing. I'm happy to try to explain and get you understand the idea. So there are a number of different ways to motivate this. So there's a couple of confusing words in this title about the derivator and setoids and things. So I know there was a talk last week about derivators. I'm not going to technically assume that you were there. I know maybe not everybody was, but let me sort of start back up at the beginning then about the motivation, or sort of what led to me being interested in this. So maybe the question to start with that I started with asking is, what is homotopy theory constructively? Well, even more basic than that, you might ask, sort of, what is homotopy theory internally in some category or topos or something like that? People who are familiar with working internally may think of sort of when we work internally, we think of doing mathematics constructively, where we sort of don't have the law of excluded middle or the axiom of choice. But for the purposes of today, you don't need to worry about the law of excluded middle. Really, all that matters is that we're trying to do homotopy theory without the axiom of choice. So the law of excluded middle is fine. Everything, all of the interesting phenomena come from not having the axiom of choice. So what the issue here is, why is this an interesting question? Well, so classical homotopy theory involving like done with like CW complexes or like simplicial sets or whatever people use for these sorts of things actually does use the axiom of choice in various places, and excluded middle as well. And there have been multiple proposals that people have put forward recently for how to do homotopy theory constructively, involving, sort of constructive simplicial sets, or maybe different kinds of cubical sets, or you might try to do something with some sort of Grothendieck sort of algebraic infinity-groupoids, and there are various other things that you could try. And in sort of classical mathematics, all these different ways of doing homotopy theory are equivalent. But in in constructive mathematics, or internally, or even without the axiom of choice, these things are really not equivalent. Apparently, anyway. I don't know whether it's entirely clear that they're not, but it certainly seemed to be not equivalent. And so that raises a natural question of sort of which is right, and sort of what does it mean to be right or correct? And that's sort of the question that I want to make a little bit of headway on, at least. I'm not going to propose an actual answer to that question, but I would like to understand at least even what that question means. So to start with, I don't want to try to explain what a simplicial set or a cubical set or an algebraic infinity groupoid is, but I can actually explain the basic idea of what's going on here and why these things aren't equivalent by just looking at sort of ordinary groupoids. Okay, so just think of like ordinary groupoids have a set of objects and sort of a bunch of isomorphisms between them that I can compose and vary, so on and so forth. And sort of classically, groupoids are a model for homotopy 1 types, if you know what that is. But you can just think of ordinary groupoids. But in sort of without the axiom of choice, some funny things happen because for instance, you may know that without the axiom of choice, we can't claim that a fully faithful and essentially surjective functor is an equivalence in the sense that it has a functor going back in the other direction. And I'm not going to engage directly with that right now, but instead I want to talk about a way in which a notion of groupoid determines a notion of set, which might end up being different for different notions of groupoid. So classically, maybe I'll say sort of over here, classically, with the axiom of choice, we have the category of sets, which sits inside the category of groupoids. And this is sort of a full embedding where each sort of set is mapped to the set with the discrete groupoid structure. And we can actually characterize the image of this embedding two categorically inside of the two category of groupoids up to equivalence by saying that a groupoid X is, you might say, bidiscrete or pseudo-discrete or essentially discrete. Well, there are different ways of saying it. I mean, here's one which I'm going to kind of like today, is to say that the equalizer in the sort of two categorical pseudo sense, so the pseudo equalizer of the two copies of the identity map of X is equivalent to X itself. So in an ordinary 1 category, the ordinary equalizer of two maps which are already equal is just the domain of those maps. So you might expect the same thing to be true here, but it isn't in a general 2 category. If you think about by a pseudo equalizer, right? I mean, this is sort of the category whose objects are objects of the domain here, X, equipped with an isomorphism from it of X to it of X. So ordinarily, in general, this equalizer is equal to what you might call like the loop groupoid of X, whose objects are objects equipped with an automorphism. And so to say that X is equivalent to that loop groupoid is essentially to say that the only automorphisms are identities. And so that is equivalent to saying that any two objects, if they're isomorphic, then that isomorphism is unique. So, what you should think of for an essentially discrete groupoid is that you've got a bunch of points and some of them are isomorphic and some of them aren't, but the ones that are isomorphic are all uniquely isomorphic to each other in sort of cliques. And nothing, there are no non-trivial automorphisms. And another name for this is an equivalence relation on the set of objects, right? Because we just say that two objects are related by the equivalence relation if there is an isomorphism between them, and it's necessarily a unique isomorphism in this case. And then, so we sort of partition the thing into equivalence classes. And so classically, this category of equivalence relations, which are sort of characterized in purely 2 categorical terms by this property, is equivalent to the category of sets. Now, without the axiom of choice, however, this isn't really true anymore. So what the essentially discrete objects of the category of groupoids are, again, these equivalence relations. So you might say sort of the category of equivalence relations. But the morphisms between two sets equipped with an equivalence relation, right? So you got x tilde and y double tilde, right? The morphism is a function from x to y, which respects the equivalence. So x is x is related to x prime, then f of x is related to f of x prime. In this case, it's no longer the case that every equivalence relation is equivalent or isomorphic in this category to a discrete one. To get it to actually, you can actually make it a one category, right? So I'm saying that this here, maybe I should say this is an equivalence, right? So by the category of equivalence relations, I mean the objects are equivalence relations and the morphisms are functions with this property, but we consider two morphisms to be equal to each other if for every x, fx is related to gx. So in the two category, this means that there is a natural isomorphism between these functors, which is necessarily unique. And so if we quotient by these, we're sort of not changing it up to equivalence or biequivalence of two categories. So the category of essentially discrete, the two category of essentially discrete groupoids is equivalent to this category of equivalence relations, which another name for this is, I'm going to write it as set sub reg. And I'll say what that means in a minute. But the point is that this is not equivalent without the axiom of choice to the category of sets. And so this is called I call this set reg because this is the free regular completion of the category of sets. So to explain what that means, let me recall or remind you or define a little bit about regularity and exactness. So if I have a category E, which has finite limits, then we say that it's regular if it has pullback stable images, image factorizations. I can't spell pullback stable images, where I mean an image means that every map factors as a regular epimorphism followed by a monomorphism. And then it's furthermore beyond that, it's exact if it's regular and every internal equivalence relation is effective, meaning that it is the kernel pair of something. So if I have an internal equivalence relation, so this is a subobject of x cross x with some transitivity and properties, then I can consider the coequalizer of this equivalence relation, and then effective means that I get R again if I pull it back over these. If I pull this quotient map back along itself, then I get the original relation. So in sets, this means that 2 points become equal in the quotient of an equivalence relation precisely when they were already related by the equivalence relation. So there's a category of there's a two category of exact categories and a two category of regular categories, and they forget down to the category of categories with finite limits, and they each have left adjoints in some two categorical sense. And this is what I mean by this subreg means the free regular completion of a category with finite limits. And there's also this free exact completion of a category with finite limits. We'll go all the way back up to exact categories. So yeah.
Can I ask this?
Yes.
Isn't take a category, then a C, then set to the C app is complete or co-complete, and isn't that the Yoneda lemma? So so this is more complete or harder to be less complete?
This is less complete. These can actually be constructed if you take E and you embed it in its presheaf category by the Oneida embedding,
Right.
then let me see if I get this right. So the exact completion and the regular completion sit inside here. So the regular completion is equivalent to the subcategory of the presheaf category consisting of the images of maps between representables. So you literally take the representable object presheaves and you close them up under taking images inside the presheaf category, and you get the regular completion. And then to get the exact completion, you also close them up under taking quotients of equivalence relations.
Okay, but and the Oneida lemma says that anything, any sheaf, any presheaf is is made up of representables, no? Or...
Every presheaf is a colimit of representables. So it's a quotient of an equivalence relation on some coproduct of representables.
Okay. So you're restricting methods of how to find those elements. Those. Okay, I understand. So you're not looking at just colimits. You're looking at special types of colimits.
Exactly. Yeah.
Okay. So now, okay, fine. Now it makes sense.
Yeah. There's a very precise sense in which this is sort of a unary version of the Oneida lemma or of the presheaf category. The presheaf category is an infinitary exact completion, and this is a one-vary version.
One-vary as in finitary, or as in somehow this is intuitionism?
No, it's like this. Okay, so if I fix some cardinal number kappa, then there's a notion of a kappa regular category or a kappa exact category,
right?
Which is basically these properties plus kappa small coproducts, or nice kappa small coproducts, which are like extensive or whatever you call it. And if you take kappa to be the size of the universe, like the proper class ordinal, then the ORD exact completion is equal to the presheaf category. So what we're saying here is that sort of we've got the regularity and exactness is just a property like this, where you sort of drop this completely, or equivalently, you sort of only have coproducts of single objects.
Oh, so K is equal to 1.
Not quite, because K is equal to 1, then that would also allow coproducts of 0 objects. In other words, having an initial object, and we don't even have that. But it's very much like taking K equal 1.
Okay. And to some extent, so this irregular is the category of groupoids, special groupoids, where each blob is continuous contractible. So your objects of your sets are blobs.
Yes, that's right. Blobs. Yes, the idea. So every connected component is contractible.
I have a question. So this is equivalent to just a groupoid having pi1 equal to 0, right?
Every pi1 equaling 0.
Every pi1. And that's true constructively too?
Yeah.
Okay, cool. Thanks.
But the thing that's not true constructively is that if you have an X like this, then it's not equivalent to the set pi0 of it. Because there's a map from X to the set of connected components, but to have a map backwards is like the X of the choice. It's choosing an element of each equivalence class.
So constructively, it still gives like the same class of such groupoids, but they're not equivalent to the underlying sets.
Right, exactly.
Gotcha.
So, so you have set sort of these groupoid things sitting inside the category of groupoids. you have, maybe I should, you have set, and then that sits inside groupoids, but then you also have sort of set reg that sits inside groupoids like this. And the point is sort of somehow these guys are the ones that are sort of the two categorically natural discrete objects. Because there's the ones that have this sort of property here that you can characterize them in terms of two categorical limits.
But classically, I mean, set is a regular category.
Even constructively, set is a regular category.
But completion isn't like the same thing?
It's the completion is not the same thing because this adjunction is not idempotent.
Okay.
Right? Just like set is a co-complete category, but it's not equivalent to its presheaf category. So in fact, it is true that the statement that set is equivalent to its regular completion is equivalent to the axiom of choice.
Wow,
that's cool.
Yeah, that's. Is there a two categorical way of characterizing set, even one that you don't, you wouldn't like because it doesn't have, inclusivistic?
I don't know of inside of groupoid, you mean?
Right.
I don't know of a two categorical characterization in the sense of being invariant under equivalence and stuff. Like if you remember that it's a strict two category and you're willing to use sort of properties of the underlying strict one category, then you can probably do
it. Can I do it regular? I think of groupoid anyways as the category of groupoids as a one category. So can I describe set from that?
Oh, probably.
It's not important.
Yeah, not very important, but I expect probably. Okay. Right. So this is sort of the idea of what's going on, why there's an issue. So in a sense, you have this notion of groupoid, which is sort of this natural, obvious, naive version of groupoid, but then you don't get back the ordinary notion of set as the sort of the discrete objects. But then there are also other notions of set. There's this exact completion also. So the objects of the regular completion are these equivalence relations. The objects of the exact completion are what are sometimes called pseudo-equivalence relations. Unfortunately, this pseudo has nothing to do with the two categorical pseudo of up to isomorphism. What it means here is that it's like an equivalence relation, but it's not mono anymore. So you have an X, and then you have an R that maps to X cross X, and you have like transitivity and reflexivity and symmetry. But this thing here is not necessarily a mono anymore. So in a sense, like two things might be related in more than one way, rather than just being a property. And then you have like the morphisms and so on are defined in a similar way. So these objects are also what are called, so maybe I should say, the objects of the exact completion of set are what are called setoids. And this terminology comes from type theory, where you start from something like Martin-Lev type theory, where you don't have a notion of quotient. So you can't like take the quotient of a type by an equivalence relation. Then if you want to have a notion of quotient, then what you do is you take the category of types, which doesn't have quotients, but it does have finite limits. And then you do this exact completion to it, and because you want to have an exact category. And then you call those objects setoids. But you can do it to any category. You can do it to the category of sets, and you get a reasonable notion also. But it's not, right, constructively, it's not the same as the category of sets. So I guess so maybe the what I wanted to say here as motivation was that where does this exact completion come in? So if you believe that sort of suppose you look at this fact that you get set reg inside of groupoid and you think, well, maybe set reg is sort of a better notion of set, then you might think, well, maybe a groupoid should have hom objects in set reg instead of set. And so you can do that. You can define what you might call like an R groupoid or a reg groupoid, which is maybe you might say like a set reg enriched thing. Category groupoid in some sense. And then if you do that, then what you get is that you might say, well, what are the essentially discrete objects in here? And it turns out that those are the pseudo equivalence relations. It's these setoids in the exact completion. So there's all sorts of different kinds of groupoids that you might consider, and you can go on and take like E groupoids, which are groupoids that have a setoid of objects, a setoid of morphisms between any two things. And it actually stops here, so that the essentially discrete objects in E groupoids are already set X again. So in some sense, it stabilizes. But it's a little bit weird that you start from you feel like you know what sets are, and then you just want to do homotopy theory, you want to do category theory, but then you find yourself forced into these other worlds. And so the natural question that I'd like to answer or think about is sort of which is correct, or maybe which is better. Do we care about things like, do we care about groupoids, or do we care about R groupoids, or do we care about E groupoids? And maybe do we need these sort of setoid things to do homotopy theory constructively or without the axiom of choice? Can we avoid them somehow, or are they sort of unavoidable?
Can I say something? I would understand where these pseudo equivalence relations would be liked by proof theorists. In other words, there are two objects, and there might be different proofs showing that these two objects are the same.
Yeah.
And so this corresponds to exactness, and the regular is regular equivalence relations.
Yeah.
Okay, and in set, it's either 1 or 0 in some sense. You know.
An equivalence relation, right? Yeah, everything is either related in one way or not at all.
Right. Okay, so
still being excluded middle.
Right. So you have these like 3 different ways of looking at how two objects are related to each other.
Mm-hmm.
Either they are related or not. Either there's a proof of them, or okay, fine,
or they're identical.
Or they're identical, right?
Yeah. Yeah. Exactly. Okay. So
at some point you're gonna have to mention the word derivator.
That's right. That's mine. That was what I was gonna write the next time. Okay, derivator. So why do where do the derivators come from? Okay, so what does it mean to do homotopy theory? What is homotopy theory? Different people answer this in different ways. Nowadays it's sort of fashionable to say that homotopy theory is about infinity categories. A little longer ago, it was more fashionable to say it was about Quillen model categories. But today, I want to say that homotopy theory is about these things called derivators. And the reason that I prefer that is that it doesn't, it allows us to work to express good universal properties of homotopy theories without sort of presupposing that we know what an infinite category is. So what's the universal property that I want to express? So there's it's a big generalization of the fact that the category of sets is what you might call the free co-completion of a point. And so by that, what I mean is that for any co-complete category, say C, the category of co-continuous functors from set to C is just equivalent to C itself, because it's determined by the image of a one-point set. And everything else follows by co-continuity, because every set is essentially uniquely a co-limit of one-point sets.
This is again the Uniter lemma.
Exactly, right. So set is set to the I don't know, one up maybe, right? The preceives on the point, and then it's the free co-completion of that. So classically, the homotopy theory of topological spaces or simplicial sets, that's sort of the standard homotopy theory, is the free co-completion of a point in this sense among homotopy theories, right? So I want to write the same thing, right? So, and for any co-complete homotopy theory, C, the co-continuous maps of homotopy theories from hot to C are equivalent to just C itself. And what is that? So what the question is sort of, what does that mean, right? So this is true if by homotopy theory you mean infinity category. And then this sort of means infinity functor. And this means infinity equivalence. I should use the same color for that. And so, but the problem with that is that in order to, defining an infinity category has sort of Hom spaces in homotopy theoretic spaces. And so defining an infinity category, knowing what the right notion of infinity category is even harder than knowing what the right notion of homotopy theory is. And so that sort of doesn't really solve our problem of figuring it out constructively. We could also, unfortunately, it sort of doesn't really work to take Quillen model categories. I mean, you sort of maybe, but it sort of doesn't really work all that well to talk about like you don't have a model category of morphisms of model categories. I mean, you can sort of try to futz around with stuff, but it doesn't work nearly as nicely. But it does work with these things called derivators. And in this case, this is just a map of derivators. And then this is an equivalence of derivators. And the nice thing about derivators is that the collection of derivators is just a two category. And so this is really just an equivalence in a two category, which is something we feel like we understand. We don't have to go up to like infinity world or something like that. So this sort of gives us a way to ask the question, sort of what is the free co-completion of a point in the world of derivators, where we can define a derivator only knowing what two categories are, and we can define a derivator and then say, is there a free co-completion of a point? And if so, that's a good candidate for what should be sort of the standard homotopy theory. So that's why I'm interested in derivators. So what is a derivator? Okay, so we need to be a little bit careful formulating the definition in a way that is correct constructively or without the axiom of choice. It ends up looking very similar to the classical definition, but I'm just going to write them side by side so that you can see that there's a little bit of change, but it's not a whole lot. So the basic notion, maybe I'll call this like axiom 0, is that we have a functor maybe D, from the two category, this is a two functor, of small categories to the two category of large categories, which is contravariant. And the example, the fundamental example you should keep in mind is that for an ordinary category E, we can define sort of D of E or whatever of some small category A to be the functor category from A to E. And some people whose minds have been corrupted by too much cohomology like to take A op here, and then the functor goes from the double dual cat co-op into cat. But I find it more natural to think about covariant functors than about contravariant functors. So I like to think about it to do it this way. I mean, you can reformulate all the axioms in an equivalent way, one way or the other way. So that's the basic idea, is we sort of collecting the information, not just of a category, but of all these sort of categories of diagrams in that category of all different shapes. And the two categorical action of this is given by essentially by precomposition, right? So if I have a functor U from A to B, then I have precomposition with U that goes from diagrams in B to diagrams in A. So that's the basic structure. This sort of thing is called a pre-derivator. And then we put a bunch of axioms on it. Let's see if I can fit these all on here. Right, and I'm going to write the classical version on the left and the constructive version on the right. So the first axiom is some kind of a sort of a stack condition, which classically says that if I have some coproduct of categories, then a diagram of that shape is naturally equivalent to a product, right, a tuple of diagrams of the individual shapes. Maybe I'll say I belongs to some indexing set. Okay, so this is true, right? Because here in this case up here, because I'm just mapping out of a coproduct, and so it's just the usual universal property of a coproduct. Constructively, or without the axiom of choice, we can assert the same thing, but only if the indexing set I is special. And you might sort of this make a little bit of sense, but if you think about the axiom of choice, right? The axiom of choice is about saying that a product of non-empty sets is non-empty, indexed by some arbitrary set. And so here we've got products indexed by arbitrary sets, and it makes sense that things are going to get a little weird if we don't have the axiom of choice. So it's certainly true if I is reasonable to assert it if I is finite. And more generally, it's actually, you can also assert it if I is projective, which basically means that products indexed by I do satisfy the axiom of choice. So all finite sets are projective, but there are some others. Maybe there might be others also. So we could choose either of those in our definition, then we get a sensible notion. It turns out that turns out to be sort of good enough for most purposes, pretty much everything we need. So that's one sort of basic thing, which basically says that so we can sort of break up diagrams into pieces if they're sort of disjoint from each other. The second axiom says that if I consider a category A, then for any object of the category, I can sort of consider A as a map from a one-point category into A. Little a is a functor from the one-point category into A, and then there's a corresponding restriction map that right coming from up like up here, the functoriality property, and that goes down to D of a point, and then I can take the product of all those maps, mapping into the product, the tuple of all those maps, mapping into the product of the copies of D of a point. And this functor, I mean, obviously it's not an equivalence because it's just remembering the action on objects and the components of natural transformations. It's not an equivalence even for these sort of represented versions. But what we can say is that it is conservative, which means isomorphism reflecting. And in the represented case, this says that if a natural transformation is pointwise an isomorphism, then it is a natural isomorphism. It has an inverse, which is also a natural transformation. So that's the classical axiom for there. And we use that a lot of times in the theory of derivators to show that certain diagrams are isomorphic by sort of evaluating them at points and then seeing what happens. Constructively, we can't assert that same thing because, again, there's some sort of product over here of a bunch of things in A. And again, you can sort of expect that to be weird if we don't have the axiom of choice. But it turns out that what is sort of good enough and for pretty much all purposes is to instead say that we consider the functor from the discrete category on the objects of A into A. So let's call that IA maybe. And then we can restrict along that functor to get to D of A0. So A0 is just a discrete set regarded as a category. And we can say that this functor is conservative. The difference between these two versions of the second axiom vanishes in the presence of the classical first axiom, right? Because sort of classically, over here in the classical world, this guy here is actually equivalent to D of A0 because A0 is a coproduct of a bunch of copies of the point indexed by the objects of A. And so the der1 in the classical case shows that these are equivalent. And so these axioms are the same. But constructively, it sort of works better to work with D of A0. There's a point here which I don't want to belabor or spend a long time on, but if you know what an indexed category is, or if you've done any sort of category theory constructively or thought about it like that, then you may have encountered this idea of an indexed category. So the idea is that or category theory over a base topos, for instance, then we often talk about indexed categories which are not just an ordinary category, but they come with a basic notion of I-indexed family of objects when I is an object of the base topos or sort of internally a set. And so what the idea, maybe another way to phrase the idea going on here is that a derivator has an underlying set indexed category. And sort of this axiom here is about the relationship of D to its underlying set indexed category. You can think of a constructive derivator as an enhancement of a set indexed category that includes sort of indexing by categories as well as indexing by sets. And in the classical case, sort of indexing by sets becomes trivial by this sort of product property. But in the constructive case, we still need to keep the indexing around. I haven't heard any questions, so I'm going on, but please ask if anything is unclear. So those are the two sort of stacky-like conditions on a derivator. And then the last two are about the existence of limits and colimits, or more generally, left and right conextensions. So the der3 tells us that we have these conextensions. So each maybe for each u functor in cat, this u star functor that goes from d of b to d of a has both adjoints, which are sometimes written as u shriek, u lower shriek, u lower exclamation mark as the left adjoint, and u lower star as the right adjoint. And you should think about this u lower shriek as basically like left conextension along u, homotopy left conextension, and this is sort of homotopy right conextension. In particular, right, in the case when if B is a point, we get homotopy limits and homotopy colimits as left and right adjoints to the diagonal functor, the constant diagram functor. And this axiom requires no change at all in the constructive version. We just assert exactly the same axiom. Wow. And then the final axiom, I don't want to say a whole lot about it, but it basically says that there's a pointwise formula for these things, these Kahn extensions, right? So in an ordinary category theory, a Kahn extension is pointwise if it's given by a formula computing it in terms of colimits or limits. And so we basically exert a version of that for these adjoints here. And similarly, in the constructive version, we basically do sort of an indexed version of that, which is sort of similar to DARE2, where we use this A0 instead of sort of all objects separately. So I don't want to state that precisely for time reasons, but we can talk about it later if you want. So that's a derivator. Yeah.
Is there a deeper relationship between derivators and stacks, or is it just an analogy?
That's an interesting question. So the thing about a derivator is that the interesting, or sort of the non-trivial ones, like the ones that don't come from this sort of construction up here, these the represented ones, are not stacks in any sort of non-trivial way because they've been quotiented. So the derivators come from you do some sort of localization, or you sort of quotient by homotopy equivalence, and then either you start with something that satisfies some stack condition, but then it no longer satisfies that stack condition on the nose. So you can kind of think of sort of these DARE1 and DARE2 as sort of like the leftovers, the leftover shadow of a stack condition.
Yeah, because it kind of reminded me of like descent
on homotopy. Yeah, on homotopy categories. If I have a stack of categories and I have like weak equivalences, a stack of categories with weak equivalences, and I localize them pointwise, then I don't have a stack anymore. But I sort of still have sort of some shadow relationship of what used to be a stack, and now sort of this is what's left. That's how I think about it.
Very cool. Thank you.
Okay, great. So let's see. What do I want to say here? Okay, that's fine. I don't want to go too much longer than an hour. Let me let me sort of state the main result here then. Okay, so here's maybe a theorem, which is constructive. So it doesn't use the axiom of choice or the law of excluded middle or anything like that, which is that the exact completion of the category of sets and the regular completion of the category of sets are derivators. So maybe that's one theorem, and I mean obviously I'm not going to prove the whole theorem, but I want to give a little bit of idea what's going on. So what is so there are different ways to get a derivator. So one way is this sort of represented version that I wrote in blue up here, and another version which I think was the speaker last week talked about was if you have a category with weak equivalences of some kind, like a model category or something like that, then you can consider the represented derivator on that, and then you can invert the pointwise weak equivalences in all these functor categories. And then under good conditions, you'll get a derivator that way. But the better examples that I like to think about, which is in many cases equivalent to this localization, but I prefer to think about this category D of A as consisting of sort of coherent diagrams. In the sense that if we're like if we're in a homotopy theory, then a coherent diagram means that I have some objects and I have some morphisms, and then all the squares and triangles and so on in my diagram don't literally commute, but they commute up to a specified isomorphism or to a specified homotopy. And then sort of on higher dimensional things, those homotopies compose up to some higher homotopy and so on and so forth. That's the way it is in an arbitrarily high dimensional homotopy theory. But in the case of this sort of exact completion, there is no sort of higher dimensionality, but there is at least that one level of coherence that we can ask for. So what is a coherent diagram in this case? So it consists of the following. We have sort of for every object of A, we have a setoid, a pseudo-equivalence relation X. And then for every morphism, say A0 to A1, alpha, we have a map from sort of, there's an X, maybe I'll say, which has a relation on it, like maybe I'll say sort of a X twiddle or something. And then maybe this is sort of A0. Maybe I should call this RA0. And then there's an XA1, which has its sort of pseudo-equivalence relation on it. And then this map consists of a morphism, the X alpha, between these sets, a function between these sets, together with a function between these representing sets of relations, which sort of commutes with various stuff. And then there's some sort of witnesses that if I have sort of an XA0 going to XA1, going to XA2, and then sort of I have alpha, X alpha and X beta, and then X of the composite, beta alpha, that these composites aren't literally equal, but they're equivalent in the sense that sort of X beta of X alpha of some little X is equivalent in this sort of pseudo-equivalence relation to X beta alpha of X with a specified witness. So this is sort of like the proof theorist version of a function that respects equivalence relations. You don't just say there exists a relation here, but there's a specified witness of it. And similarly, these R's are saying that if X is related to Y, then X alpha of little x is related to X alpha of little y in a specified way. So if I had the axiom of choice, then I could choose these specified witnesses arbitrarily whenever even if I didn't have them. But if I don't have the axiom of choice, then requiring them to all be given at once is a stronger statement than just asserting that they exist pointwise. So this is sort of with the axiom of choice, then this category here is actually equivalent to the ordinary functor category from A into the exact completion of set, but in general it isn't. It's something different, but it still makes this thing into a derivator. And sort of constructively, without the axiom of choice, this guy is better because without the axiom of choice, this sort of ordinary thing is not complete and co-complete as a category. It has finite limits, but in order to construct infinite limits or infinite co-limits in this category, you basically need to make choices because the morphisms are sort of quotiented. They sort of say that these witnesses exist rather than that they're given. So this sort of set X is not a very good category all on its own constructively, but we can enhance it to a derivator and it becomes a very nice derivator. So that's the first theorem that I wanted to state. And then let me just state one more theorem and then I'll be done and I'll take questions, which is sort of the main point here. why this is interesting and why it sort of goes some way towards answering the questions that I raised at the beginning. Right. So yeah, the theorem maybe is well, okay, I'll state it and then I'll explain the term in it that's not in there. So the theorem is that the exact completion of set and the regular completion of set, maybe I'll say, and also the category of sets, are relative free co-completions of a point. And what that means is that they have this property, which is that for any co-complete derivator D, I'll just state this property for set X. And this derivator is what's called set X local. Then we have this property that the co-continuous maps from this derivator set X into D are equivalent to D itself. Or maybe if I just consider this as a category, then it's just sort of D of a point, the objects of D. Right. And I didn't say what sort of set local is, but the idea of this is sort of, you can say, well, the category, right? So the category homotopy theory is a free co-completion of a point in sort of homotopy theories or sort of infinity categories. And the category set classically is a free co-completion of a point in one categories, but one categories sit inside homotopy theories as sort of the discrete objects, sort of the locally discrete ones, right? They're like infinity categories where all the Hom spaces are sort of discrete in some sense, classically. And so you can say you can sort of determine this subcategory here based on knowing what set is. And so there's basically what happens here is that you have set and you have set reg and you have set X, and each of them has a corresponding notion of sort of what you might call one categories. Sitting inside homotopy theories, derivators. And each of them is a free co-completion of a point in that world, the corresponding notion of one category. So in that sense, sort of there are three arguably equally sensible notions of set and notion of one category sitting inside homotopy theory. And these things each have that corresponding property. And the conclusion from that may be about the sort of the global case is that because we have because sort of set sits inside these larger ones, if there is a constructively, if there is a homotopy theory that that is an absolute free co-completion of a point, in the sense that it satisfies this for all derivators, then it sort of must include also all these relative free co-completions of a point. So not just set, but also set reg and also set X must live inside this world of homotopy theory. So in that sense, at least for this notion of homotopy theory and co-completeness and this sort of universal property, this basically says that from this perspective, we can't avoid setoids in constructive homotopy theory. If the notion of homotopy theory is such that it is going to be a free co-completion of a point in this world of derivators, which is at least a sensible thing to want, You could argue that maybe it's the wrong thing to want, but at least it's a sensible thing to want to try to get something which is analogous to what happens classically with the axiom of choice. Then in that case, you can't avoid the setoids, that they're sort of necessarily going to sit there inside your standard homotopy theory. All right, maybe I'll stop there. And if you want to know more about any of this stuff, you can ask questions.
Thank you. Let's thank the speaker. Wow. It's a lot to gather. Anyways,
yes.
Are there any questions?
Yeah, so oh, sorry. Just wondering, is this is your motivation for this work for semantics for homotopy type theory?
He always asks me questions like that. I am actually interested in things other than homotopy type theory. I don't expect that derivators themselves will have any application to semantics of type theory, because they're much too flabby to actually interpret type theory. You need something more like a equivalent model category. I did sort of start thinking about this because I was thinking about models of type theory, and so in particular, like these examples that I mentioned here have been studied constructively as models of type theory, and I guess it's unclear. Some of them are models and some of them aren't, and it's sort of a question of sort of whether they're equivalent to each other and which one is the right version. And so there's sort of this observation that they're not equivalent, and sort of sitting inside them is these sort of setoids. Excuse me. Maybe this is part of what led me to wonder about whether the setoids sort of have to be there in a notion of homotopy theory constructively, or whether you can get away from them. But I don't expect it to have direct applications to that, but maybe it sort of informs our choice or expectation of what kind of models we expect to have, if that makes sense.
Thank you.
The last part of the argument would seem to be the key bit on why they have to be there. I think I missed a step in the argument, in a sense, because
I left out a lot of steps.
Well, not in the technical details, but conceptually, right? So posit I've got really anything that's classical and involves set. And then what you've got is these you've got things that are classically equivalent to set, but like at least set red, right? But well, I guess in set X that but constructively fragment, and then you get on some level at least half of this phenomena already, because so I guess that's what I'm trying to follow is, morally, why do setoids have to be there more than they have to be there for any other use of set at all once you go constructive?
Well, in a lot of places, when you do constructive mathematics, you can stick to sets. Very little, if anything, forces you to introduce setoids. Whereby constructive, I mean something like a constructive theory that has quotients already, like IZF set theory, or some sort of extensional type theory with quotient types, or something like that. Right? I mean, if you start from something like Martin-Luff type theory, plain Martin-Luff type theory without quotients, then of course, if you do need to do reasonable mathematics, you need to have some kind of quotients, and so you need to throw them in freely and work with setoids. But if you start from a notion of constructive mathematics that has quotients, then there's very little which will force you to talk about setoids. You can just use the quotients that you already have. So what's happening here that's different is that we didn't choose to work with setoids. We define derivators, we define categories to have a set of objects, not a setoid, and a sets of morphisms, not setoids. We define the two category of categories in a direct way using sets, not setoids. We defined derivators. The notion of derivator is defined using categories and sets, no setoids put in. And yet, nevertheless, if we ask sort of what is the derivator that has the universal property of being the free co-completion of a point, it turns out to be setoids, even though we didn't choose to put in any setoids.
Okay.
I have a question. So we have this equivalence classically, I think, between exact categories and definable subcategories.
And what?
We I think it's in a paper. There's an equivalence between definable subcategories and exact categories, right?
Definable subcategories of what?
Well, I guess definable categories. So anything equivalent to some definable subcategory.
Of what?
Of a locally finitely presentable category.
Are you using the same notion of exactness that I am? I mean, because a locally finitely presentable category doesn't have to be exact. And it's certainly a definable subcategory of itself.
Maybe I'm using a different notion of definable subcategory.
What is a definable subcategory?
Pure subobjects, all co-limits, and I think product. Hold on.
I just while we're waiting for him, Diago, you're online. We were talking before about your slides. Is there a way we can get if you email me your slides, I'll post them online because some people want them.
Oh, yeah, of course I can do this.
Okay, so good. So send us your slides. Send me your slides and I'll post it.
Okay. All right.
Okay. Thank you.
Yeah, products, directed co-limits, and pure subobjects.
You mean closed under those things?
Yeah.
Okay, but the whole category is certainly closed under those things.
Yes, but yes. So yeah. I think it still works, right? And
But a locally presentable category itself is not necessarily exact.
well, it's not necessarily exact, but there is an equivalence which sends it to an exact category.
Okay, I'm not familiar with this. What is I mean?
Yeah, I guess my question was whether this is a constructive result as well. I don't.
Okay, I'm not familiar with it. I kind of doubt it because very little of locally presentable category theory is known to work constructively because it uses I guess locally finitely presentable is not such a big deal. It's not such a problem, but yeah, I don't know.
Can I just say two people gave two talks on derivators. It was the same definition essentially, but totally different motivations and totally different world outviews. Like sketches of an elephant, which makes it fascinating, absolutely fascinating.
There is a point of contact, I think, because I haven't completely understood this. I think I'll need to look at the slides from last week when they're available. But I remember I started asking about what is homotopy theory internally in some category, in some topos. And I think that is probably related to what Diago was saying last week.
Right. He asked what's homotopy theory intrinsically?
Right. So I guess maybe I'm sort of thinking about the classical, sort of the standard homotopy theory. And he was thinking about if you start from some general homotopy theory, how you would make it intrinsic. So this would be sort of starting with the standard one, like simplicial sets or whatever you want to do, and then making that intrinsic. Is that necessarily the right answer in this sort of sense of being a free co-completion of a point, and how can we tell? So it's not totally unrelated, I think.
Tiago, do you have anything to say? Do you?
Yeah, I guess they are related in some sense. My motivation was more like my attempt is more like trying to internalize a general, or at least a suitable homotopy theory presentable by a localizer in a topos, like we have already the results for the simplicial sets, the homotopy theory of simplicial sets, or the homotopy theory of the complexes of abelian groups. So there is it's more like the problem of how do we internalize structures in a topos, which is a very complicated question. I mean, it's already hard to understand how do we internalize the representable derivators, because we have to deal with the correct notion of what is a sheaf over a topos with values in an arbitrary category. And this is not so easy. So it's more like in the sense that I'm trying to, but of course I don't think that all localizers could be internalizable. So I'm trying to figure out what would be the properties of an internalizable localizer in some sense.
Can I just say, I mean, I don't know Grothendieck's motivation at all, but Heller's motivation is also different. I mean, Heller really wanted to know what, we have axioms for homology theory. Well, he wants an axioms for homotopy theory. And I suspect Grothendieck's motivations were different also. So you have one object, basically a nice functor from small cat to cat. You have one concept, a small, and you have different people looking at this thing in different ways, for different reasons, for different motivations.
Which argues to me that it's a natural thing,
right?
It's like
right. It's like topos theory. I mean, everybody has their own reason why they study topos theory.
Yeah.
And that's absolutely amazing. Anyways, thank you very much. Any other questions? Any other unhappiness, discussions? Next week. Oh, sorry. Go, Matthew. Go.
Sorry. Yeah. Can I just ask a question? Like, I'm trying to process this concept of a derivator. So this is just like trying to understand what a derivator is. I remember from last week hearing that we should think of the values of the derivator on a small category as being like the derived category or the homotopy category for diagrams of shape, which makes sense. But is there anything about the axioms that force these values to behave anything like a homotopy category? I mean, it seems to me like they're just like the most basic thing is just to think about any category of diagrams, like what makes them homotopy category, like what in the axioms forces them to be like a homotopy category,
Well, depends a little bit on what you mean by like a homotopy category. So it's so one thing you can say is that there's this functor here. You can sort of boost that up to another functor, which is you have d of a, and that maps to the category of ordinary diagrams of shape A in the d of a point. So basically, so this is one way that I like to think about it, where this is something like a coherent diagram. And these are sort of like incoherent diagrams. Right? So you think about d of a point as being the homotopy category, and then a diagram in the homotopy category is a diagram that commutes up to unspecified homotopies, whereas something in here is a diagram that commutes up to specified coherent homotopies. And this functor here, well, the der2 says that this functor is conservative. So a map of a homotopy coherent transformation is invertible if it's pointwise invertible. But sort of apart from that, there's not a whole lot you can say in general that you would like to say. I mean, so the existence of these homotopy left and right Kohn extensions and this sort of pointwise formula is another thing that you expect to have in a homotopy category, that you have sort of limits and colimits of coherent diagrams and these other things. There's one more axiom that I didn't mention, which is sometimes added, which is called der5. I don't usually consider this part of the definition of derivator, but some people call it a strong derivator if it satisfies this axiom. This axiom says that, there are different versions of it, but it says if you take A cross the interval category, so this is the category with two objects and one morphism between them, then you can map that down to D of A, the category of ordinary arrows in that category, that diagram category. And this functor, the axiom says that this functor is, I think it's essentially surjective and full, maybe. It's possible that I got that wrong, but it's something like that, which basically says that if I have a, in the case when A equals 1, it says if I have two objects and a map in the homotopy category between them, then I can lift that to a coherent diagram of this shape, of sort of the shape of two objects and a morphism between them, which is another thing that you expect to have in a homotopy category, that like you can choose homotopies and make a coherent diagram as long as there are no coherence axioms that it has to satisfy. So I don't know if that answers your question or not, but it's sort of, we're trying to formulate general properties that are true of homotopy categories and can be expressed in this language.
Got it, thanks.
That's more in line with Heller.
Mm-hmm. Yeah, I think Heller might be the one who has a stronger version of this axiom where 2 is replaced by any finite free category. Or something like that.
Right, so something is, he would say something like cylinder objects are the same as path objects or something like that.
Mm-hmm.
Anyways, thank you very much.
Thank you for the invitation.
Milo speaking next week in person, and we'll have the video up a few hours after he speaks. You're all welcome to join. Anyways, ladies and gentlemen, it's a pleasure. Thank you.